Welcome back to the deep dive. Last time we dove headfirst into Stephen Hawking's A Brief History of Time and really wrestled with how classical physics, the stuff we see daily, just doesn't quite work for things like black holes or the very beginning.
That's right. We saw how those neat rules hit a wall when gravity gets intense, or you look at the quantum level, it really pointed towards needing something else, quantum mechanics.
Exactly. And that was really just the starting point. Today, we're going deeper. We're looking at chapters 3 and 8, focusing on the universe's origin and, its ultimate fate.
The big question.
Absolutely.
Huh.
Our mission really is to get a handle on the evidence for this idea of an expanding universe,
Mhm.
and then unpack the Big Bang itself, what it is, the initial problems people found with it, and how thinkers like Hawking tried to tackle those puzzles.
And we want to do it in a way that hopefully clicks without needing a physics degree.
Right. So let's jump in. Chapter 3, the expanding universe. You look up at night.
Hmm.
What do you see?
Mm-hmm.
Just like loads of stars.
Billions and billions, yeah. And for a long time, that, plus our sun, was pretty much it, people thought. Maybe the Milky Way was this big disk, a spiral galaxy. But then Edwin Hubble came along in the 1920s.
Hubble. Oh, right. The telescope guy. So what was his big discovery?
Well, he showed our Milky Way isn't alone, not even close. It's just one galaxy among, well, countless others, separated by these vast, vast distances of empty space.
Whoa. Okay, so how did he even measure those? He can't use a ruler, obviously.
No, no. So for nearby stars, you can use parallax, how their position seems to shift against the background as Earth moves, like your finger jumping when you switch eyes.
Okay, I know that one.
But galaxies, way too far for that. So Hubble used something called standard candles. Certain stars you see have a known intrinsic brightness, a fixed luminosity.
Like knowing how bright a 100-watt bulb should be.
Exactly. So if you see one of these stars in another galaxy and it looks dim, you know that galaxy must be really far away. The dimmer it appears, the further it is.
Clever. Okay, so he figured out where they were. How does that get us to an expanding universe?
Well, this is where it gets really interesting. Around the same time, people were looking at the light from these galaxies, splitting it into spectra, like a rainbow with a barcode.
A barcode. What, for the elements?
Yeah, the dark lines tell you what elements are in the stars emitting the light. But the weird thing was, for most galaxies, this whole pattern, this barcode, was shifted towards the red end of the spectrum.
Red shifted. What does that mean physically?
It's the Doppler effect, just with light instead of sound. You know how a siren sounds higher pitched coming toward you and lower going away?
Yeah, the sound waves get squished or stretched.
Precisely. Light waves do the same. Moving towards us, light shifts blue. Moving away, it shifts red. So seeing almost everything red shifted meant
They're all moving away from us. Everything.
almost everything, yes. And here's Hubble's massive discovery from 1929. The amount of redshift, which tells you the speed they're moving away, is directly proportional to their distance.
Wait, so the further away a galaxy is?
The faster it's speeding away from us. It wasn't just random motion. It implied the whole fabric of space itself was expanding.
Wow. Not just things moving in space, but space itself getting bigger.
Think of dots on a balloon. As you blow it up, the dots get further apart because the balloon's surface is stretching. The galaxies are the dots. Space is the balloon rubber.
Okay, that helps. That's a huge shift from a static universe. Was anyone thinking along these lines before Hubble saw this?
Amazingly, yes. Back in 1922, a Russian physicist, Alexander Friedmann, had used Einstein's general relativity. He started with just two simple assumptions. The universe looks basically the same in all directions, and that's true wherever you are.
Seems reasonable enough on a large scale anyway.
Right. And based on just those ideas, his math showed the universe couldn't be static. It had to be either expanding or contracting, years before Hubble's proof.
The theory came first. But that first assumption, the universe looks the same everywhere, isn't it kind of lumpy with galaxies here and voids there?
It definitely is lumpy on, let's say, local scales. You have clusters, superclusters. But Friedman was thinking bigger picture. If you zoom way, way out, it does look remarkably uniform, statistically speaking. Like the ocean looks smooth from a plane, even though it has waves up close.
Okay, I get that distinction.
Hmm.
Large-scale uniformity.
And that idea got this incredible, almost accidental boost in 1965. Two guys at Bell Labs, Penzias and Wilson.
Bell Labs. What were they tying?
They were working with this really sensitive microwave antenna trying to track satellites, but they kept getting this faint, persistent background hiss Noise, no matter where they pointed the antenna.
Day, night didn't matter.
Didn't matter. Same noise, all directions, all the time. It clearly wasn't coming from Earth or the sun or even our galaxy. It had to be cosmic.
A cosmic background hum. What was it?
It turned out to be the cosmic microwave background radiation, the CMB. It's essentially the leftover heat, the afterglow from the Big Bang itself.
The afterglow.
Yeah, from when the universe was incredibly hot and dense. As space expanded over billions of years, that initial fiery light got stretched out, cooled down, right into the microwave part of the spectrum.
Wow. And someone predicted this.
They had. George Gamow and later work by Dick and Peebles, based on Friedman's expanding universe idea, predicted that this relic radiation should exist, cooled to just a few degrees above absolute zero. Penzias and Wilson had found exactly what the Big Bang model predicted.
That's incredible. Accidental proof. Did they win a Nobel for that?
They absolutely did. It was huge confirmation. And the CMB is incredibly, incredibly uniform across the sky.
Almost perfectly the same temperature everywhere.
Almost. Later measurements, like from the Kobe satellite in the 90s, found tiny variations, like 1 part in 100,000. Those tiny ripples are actually super important, as we'll see, for how structures like galaxies formed.
Okay, so we have galaxies flying apart, this cosmic afterglow. The Big Bang theory is looking pretty solid. But wasn't there resistance? You mentioned Friedman's models implied this. Singularity.
Yes, the math pointed to a beginning. A point of infinite density, the Big Bang. And if the universe is expanding now, logically, it must have been smaller and denser in the past, all the way back to this starting point.
A beginning of time itself. That sounds... Well, it sounds almost religious. I can see why people might resist that.
Exactly. It felt uncomfortable for many scientists, like it needed some external cause, maybe divine intervention. This led to alternatives, most famously the steady state theory.
City-state, what is the idea there?
Proposed by Hoyle, Bondi, and Gold in '48. They suggested, yes, the universe expands, galaxies move apart, but new matter is continuously created in the gaps.
So the universe always looks roughly the same. No beginning.
That was the appeal, constant density, eternal universe. But observations started chipping away at it. Surveys of distant radio sources showed more of them far away, meaning earlier in time, than nearby, which contradicted the steady-state idea of uniformity through time.
So the universe wasn't always the same.
It seemed not, but the real killer blow was the CMB. The steady-state theory just had no good explanation for this pervasive background radiation. The Big Bang predicted it naturally, so the steady-state model pretty much faded away.
Observation wins again. But back to the singularity. Was it definitely real, or just a weird feature of the simplified math models?
Great question. Some Soviet scientists, Lifshitz and Kalatnikov, explored that. They initially thought maybe in a realistic, lumpy universe you wouldn't get a perfect singularity. But they later had to backtrack and admit that, yeah, singularity seemed to be a general feature predicted by general relativity for an expanding universe.
So Einstein's theory seemed to demand a beginning, and then Roger Penrose looked at the opposite end, right? Collapsing stars.
Yes, Penrose in the mid-60s showed mathematically that when a really massive star collapses under its own gravity, it inevitably forms a singularity, a point of infinite density hidden inside a black hole.
Where the laws of physics break down.
Essentially, yes, according to classical general relativity. And this work strongly suggested that if gravity leads to singularities when things collapse, maybe the beginning of the universe, kind of like a collapse in reverse, also involved a singularity. His work, and later stuff with Hawking, really cemented this idea of a definite beginning in time.
Okay, so Chapter 3 leaves us with this picture. An expanding universe that started from an incredibly dense point. A Big Bang. Quite a journey from a static cosmos. Now, Chapter 8 picks up on the origin and fate. What does general relativity alone say might happen in the future?
Well, based just on GR, there are basically two options tied to how much stuff is in the universe and how fast it's expanding. Either gravity eventually wins, halts the expansion, and everything collapses back into a big crunch, another singularity.
Oof, the end of time.
Or, if there isn't enough gravity, the expansion goes on forever. But even then, you still get singularities forming inside black holes as stars and galaxies collapse. So singularity seemed unavoidable, one way or another.
Grim. But you mentioned earlier, quantum mechanics might change things. Like with black holes.
Exactly. Hawking's own work showed that black holes aren't truly black. Quantum effects near the event horizon mean they should radiate energy Hawking radiation and slowly evaporate over immense timescales. They might eventually return everything that fell in.
So they're not completely one-way streets.
Apparently not, if quantum mechanics is right. And that raises a huge question. If quantum effects can kind of fuzz out the singularity in a black hole, what about the Big Bang singularity? Or a potential big crunch? Could quantum gravity eliminate these points where physics breaks down?
Which brings us to that Vatican conference story from 1981. You had to tell that one.
Ah, yes. So the Vatican hosts this cosmology conference. The Pope meets with the scientists and basically says it's fine to study the universe after the Big Bang, but don't inquire into the moment of creation itself. That's God's work.
Cool.
And Hawking had just given a talk outlining his early ideas about space-time being finite but having no boundary, no edge, which essentially eliminates the need for a moment of creation. He said later he was glad the Pope hadn't quite caught the implications.
Finite, but no boundary. Okay, we have to
Yeah.
unpack that. But first, let's quickly walk through the standard picture of what happened right after the Big Bang.
Okay, so fractions of a second in, unbelievably hot, dense soup, expanding incredibly fast. The fundamental forces start to sort of crystallize out.
Gravity, electromagnetism.
Right, and the nuclear forces. Then, within the first few minutes, conditions are right for protons and neutrons to fuse into the lightest elements, mostly hydrogen and helium, a bit of lithium. Big Bang nucleosynthesis.
Okay, got the first ingredients, then what?
Then, for maybe 380,000 years, it just keeps expanding and cooling. It's too hot for neutral atoms to form. Electrons and protons are just whizzing around in a plasma. Light can't travel far. It's opaque.
The cosmic dark ages.
Sort of, yeah. Until it cools enough down to a few thousand degrees for electrons to combine with nuclei and form stable, neutral atoms. This is called recombination. Suddenly, light can travel freely through the universe.
And that light, stretched out over billions of years, is the CMB we see today.
Exactly. That's the moment the universe became transparent.
Okay, so now we have atoms and free-flowing light. How do we get galaxies and stars?
Gravity takes over. Remember those tiny ripples in the CMB, the slight density variations? Well, regions that were just a tiny bit denser had slightly stronger gravity. They pulled in more matter, slowed their expansion relative to their surroundings, eventually stopped expanding and started to collapse.
The rich get richer, cosmically speaking.
Pretty much. And if these collapsing clouds of gas had even a little bit of spin to begin with, they'd spin faster as they shrank like an ice skater, pulling their arms in and flatten into disks. Those become spiral galaxies like ours.
And if they didn't spin much?
They might form more rounded, blobby, elliptical galaxies. Within these galaxies, clumps of gas collapse further to form stars. Stars live, fuse heavier elements, die sometimes spectacularly as supernovae, scattering those heavy elements.
Which then get incorporated into new stars and planets, like Earth.
The whole cosmic recycling program, it all fits together beautifully. But, Chapter 8 points out, the basic Big Bang model, even with all this success, leaves some major questions unanswered. Hawking lists 4 big ones.
Okay, what are the big puzzles?
First, why was the early universe so incredibly hot to begin with? The model starts there, but doesn't explain the initial heat. Second, why is it so incredibly uniform on large scales? Especially the CMB temperature. How did regions that couldn't possibly have exchanged signals back then end up at the exact same temperature?
Right, the horizon problem, like two strangers knowing the same secret without talking.
Exactly. Third, why did the universe start expanding at a rate so exquisitely close to the critical rate? The knife-edge balance between collapsing back and expanding so fast that nothing forms. Even a tiny deviation early on would have led to a drastically different, likely lifeless universe. It seems unbelievably fine-tuned.
The flatness problem. Okay, what's the fourth?
Fourth, where did those initial tiny density fluctuations, the seeds of galaxies, actually come from? General relativity doesn't explain their origin.
So heat, uniformity, flatness, and structure seeds. Big questions. This leads into talking about boundary conditions, right? What does that mean here?
Boundary conditions are like the universe's starting settings. The laws of physics tell you how things evolve given a starting point, but they don't necessarily pick the starting point itself. Was the universe just set up just right from the beginning?
He mentions trying chaotic boundary conditions, like just a random start.
Yeah, the idea was maybe any old random starting state would eventually lead to what we see. But the problem is, a truly random start would likely be super lumpy and irregular, maybe full of primordial black holes. Doesn't naturally produce the smooth, large-scale universe we observe. So that didn't seem to work.
Okay, so if not chaos, then what? This is where the anthropic principle comes in. It always feels a bit circular.
It can feel that way. There's the weak version and the strong version. The weak anthropic principle is less controversial. It just says, look, we observe the universe to be the way it is because if it were much different, we wouldn't be here to observe it.
The selection effect.
Exactly, like asking why the Earth is just the right distance from the sun for liquid water. Well, if it weren't, we wouldn't be here having this conversation on Earth. We can explain the age of the universe by saying it took about 13.8 billion years for stars to form, make heavy elements, and for life to evolve.
Okay, that makes a kind of logical sense. But the strong version.
The strong anthropic principle is more philosophical. It suggests the universe had to have properties that allow life to develop. Some even take it to mean the universe exists for us.
Which feels a bit much, like putting ourselves back at the center.
It raises huge philosophical issues. And scientifically, how do you test the idea of other universes that might exist but can't support life? It's not really science as we usually practice it.
Right. So if chaotic conditions don't work and the anthropic principle feels iffy, what's the more mainstream scientific idea? Inflation.
Inflation. Proposed in the early 80s, it's become a cornerstone of modern cosmology. The idea is that a tiny fraction of a second after the Big Bang, the universe went through this period of incredibly rapid exponential expansion, much, much faster than the expansion we see today.
An early growth spurt. A massive one. How does that help with those four big problems?
Well, take the horizon problem, why opposite sides of the sky look the same. Before inflation, the region that would become our entire observable universe was absolutely minuscule, small enough for everything to be causally connected and reach the same temperature. Inflation then stretched this tiny uniform patch to enormous size.
So it solves the uniformity issue. What about the flatness?
Inflation naturally drives the geometry of space towards flatness. Think of stretching a wrinkled sheet really, really tight. It smooths out. Inflation does that to the curvature of space, explaining why the expansion rate is so close to critical.
And the seeds of structure. Those little ripples.
Tiny quantum fluctuations, always present on the smallest scales, would have existed just before or during inflation. Inflation would have stretched these microscopic fluctuations to astronomical sizes, creating the very density variations needed to seed galaxy formation later on.
Wow, okay. Inflation seems to elegantly solve three of the big puzzles. But you mentioned different versions. Some didn't quite work.
Yeah, Alan Guth's original old inflation had issues with how the inflationary period ended smoothly. Then the new inflation model fixed that, but predicted CMB variations that were too large compared to what we observe.
So those versions are out.
Largely superseded by Andre Linz's chaotic inflation. This model is more robust. It suggests the field driving inflation could have had different random values in different places. Where it was high, inflation happened. Our universe is just one patch where inflation occurred and then ended, transitioning to the standard hot Big Bang. It fits the observations, including the CME ripples, much better.
So chaotic inflation makes it plausible that a universe like ours could arise from a wider range of starting conditions, maybe making the weak anthropic principle seem less like special pleading.
Exactly. If inflation happens naturally in many regions, maybe generating countless bubble universes with potentially different properties, then it's less surprising that we find ourselves in one suitable for life.
But even with inflation, we're still bumping up against that very initial moment, aren't we? Where quantum gravity must come in.
Precisely. Inflation happens incredibly early, but maybe not right at time zero, if such a thing even exists. To truly understand the origin, you need a theory that combines general relativity, gravity, with quantum mechanics, a quantum theory of gravity, which we don't fully have yet.
The holy grail of physics.
One of them, certainly, and this is where Hawking brings in ideas like Feynman's sum over histories.
Right, the idea that a particle takes all possible paths between 2 points.
Yeah. In quantum mechanics, you calculate probabilities by summing up contributions from all possible histories or paths. Applying this to the whole universe, to space-time itself, is the challenge. And one mathematical trick used here is imaginary time.
Imaginary time. Sounds very sci-fi. Is it real?
It's a mathematical tool, a way of rotating the time axis in calculations to make certain things work out better, especially when dealing with singularities. In imaginary time, the difference between time and space kind of blurs.
Okay. How does that help with the beginning?
It opens up the possibility, explored by Hawking and Jim Hartle, that the universe, when described using imaginary time, could be finite in extent but have no boundary, no edge, no beginning point or singularity.
Finite but no boundary. Like the surface of the Earth. It has a finite area, but no edge you can fall off.
That's the classic analogy. If the universe has no boundary in imaginary time, then maybe there's no need for initial conditions to be set at a boundary. The laws of physics could hold everywhere, always. The universe would just be.
So the Big Bang singularity, that point of infinite density in real time, might not be a true beginning, but more like the North Pole on Earth, a point defined by the coordinate system, but not a physical edge.
That's the implication of the no boundary proposal. The concept of time beginning might be an artifact of looking at the universe only in real time. The universe might not have had a beginning in that singular sense.
Wow. That fundamentally shifts how you think about creation or origin. Okay, so wrapping up this part of our deep dive, we've seen compelling evidence, redshift CMB, for an expanding universe starting hot and dense.
Check. The Big Bang model.
But it had puzzles: uniformity, flatness, heat, structure seeds.
Which led to the theory of inflation, a period of super rapid expansion that seems to solve many of those issues naturally.
And pushing further back to the very origin requires quantum gravity, leading to mind-bending ideas like imaginary time and a universe possibly without a true boundary or beginning.
It's an ongoing quest, constantly pushing the limits of observation and theory. The search for that complete quantum theory of gravity is still one of the biggest challenges.
It really is. So here's that final thought to leave everyone with. If the universe, in this imaginary time view, might be finite but boundless, does our everyday notion of a distinct beginning even make sense at the deepest level? What does that say about time itself? Maybe something to ponder until next time. Thanks for joining us on The Deep Dive.